In Chapter 11, we look at regression and correlation analysis. When a single variable is used to predict another variable, we refer to a simple linear regression model. There are some other methods that we have multiple variables used to predict a response variable in multiple regression. But the idea here is the researcher has several columns of information and we're looking for an association among them. It could be that 1 or 2 is a good predictor of a third, or just how are these related? Are they linearly related or not? So we're going to do a simple overview of simple linear regression and correlation analysis, and how do we use SAS to do that. In simple linear regression, we talk about the x that's used to predict something that's going to be our independent variable, y is our dependent variable or our response, beta 0 is the y-intercept, and beta 1 is the slope. And then we have a random error associated with each ordered pair, and that's given by epsilon. We can estimate beta 0, we call that estimate beta 0 hat, and we can estimate beta 1, we call that beta 1 hat. And so that if we put the beta 0 hat and the beta 1 hat times x, we compute this, we get the predicted value of y, which we call y hat. So we were interested in how do we get these estimates beta 0 hat, beta 1 hat, and how do we get the prediction of a yi hat. The other part, there's a language that says, is this slope significant? And by that we mean, is it significantly non-zero? Lines with zero slope are horizontal. And if it has a zero slope, then x isn't helping our predictive ability of y. And so far, what our best predictor of y has been y bar, and that's what it would be in this case if the beta 1 value is estimated to be 0. There are tests for the slope for whether or not that slope is significant, and like I said, that generally means significantly non-zero. And so we take the estimator of the slope and divide it by its standard error, and with normal assumptions on our errors terms, then we have a t-statistic. These can be done also by an f-test and so the degrees of freedom for t in the simple linear regression are equal to n minus 2. For the t if we square that value of t, it is an f statistic with one numerator, and its denominator degrees of freedom is the same as that for t. We can also look at confidence intervals for any of our parameter estimates. So this form here, beta I divided by its standard error, this is actually applicable to slopes or the y-intercept. You can also test for whether it differs from any non-zero value by specifying this value b sub 0, and whether maybe you're interested in whether or not the slope is some nominal value, say 5, then you're going to have your estimated slope minus that nominal value 5 and divide it here. The confidence interval would be the same, and does it capture that beta 0 value? These are generically written as I, so we can look at even for those of you familiar with multiple regression, the process is the same as that you're testing that slope or that parameter estimate divided by its standard error, or for any one of them you can compare it to a nominal value. So in our case, for simple linear, can be 0 or 1, but if you have more than one predictor variable, this is applicable there as well. Your degrees of freedom would change for those applications, however. In simple linear regression, we can also look at the point prediction y hat, which is given here for a particular value x0, and then we refer to a confidence interval for the mean response of the y variable given an x. For simple linear regression, it is this formula. We also talk about prediction intervals, that is, say for the next observed x value of UC, what would you predict for its y? And so it's a little wider interval. There are also multiple regression extensions of these. The formulas are not given here. We are using the MSE from the analysis of variance table and in regression analysis to figure these standard errors for the predictors. To look at a regression analysis, either simple linear regression or multiple regression, we use the reg procedure in SAS. And so we have a proc reg, a model statement. Optional statements are the ID statement and the test statement. This label on the model statement is optional. I very often don't use it. I probably don't use it more often than I do. The order here is important in the model statement. Your dependent or y's equal the independent. If you reverse those, you will get an answer, but it's not the answer to the question you're asking. The ID variables, we'll talk about that in some of the output. We typically choose one or more of the regressor variables to be ID variables, and then we can also talk about testing hypotheses about the slope using a test equation in the reg procedure. As with all procedures we've looked at so far, by and where statements can be included. Just remember, if you use a by statement, it must be compatibly sorted prior to the procedure. And where statements, you can either exclude or include statements based on the condition or conditions specified in a where statement, and where those were detailed in data step information 2, which was in chapter 4. You can add options to the proc reg statement here, and back to kind of what we saw in some of the earlier procedures, there are plot options there. And so anytime you see these vertical bars, pick one plot option here, and these then, so if you want to suppress them all, if you want to look at diagnostics, or if you just want to see the fit of the equation, these will produce ODS graphics. These last two, of course, none means that all those are turned off. Sometimes the diagnostics are panel graphs, and so you can unpack those to get larger graphs of any one of the images it produces. Additionally, on the proc reg statement is a simple option, simple statistics for each variable in the model. That's both independent and dependent variables in there, so you'll get values for some of the x's, some of the y's, their means, and so forth. The model statement, just as I said before, you want to remember it's always order important. So it's dependent equals independent. You can specify multiple simple linear regression here. So this is X being used as a predictor for, say, A, B, and C. You can stack up things on the left side also, and you can specify more than one model statement in the regression procedure. And for most of the things we're going to do, we wouldn't necessarily do that, but if you do put more than one model statement in a procedure, then that label option is a good idea. Recall I spoke about confidence intervals both for beta, the mean response for y, and for prediction intervals. And so those requests are all available on the model statement, kind of working from the bottom up here. P requests the predicted values or the y hat values for each of the observed x's. They aren't printed by default, so you have to ask for those. CLB is the confidence limits for the betas, the y-intercept and the slope. If you want something other than 95%, then you need to write alpha equals and specify the probability you want there. So by default, you're going to get 95% confidence intervals. The confidence interval for the mean response and the prediction interval. Again, 1 alpha controls all of those. There are a few options listed here for those of you that might be taking a regression class and looking at multiple regression. These are certainly selected statements that you would like to become familiar with in working with multiple regression. If we request predicted values or any of those confidence intervals or prediction intervals for the mean output in the output, it's very difficult to read unless you use an ID statement, and so that'll come up, and I'll talk about that a little more specifically in the objective. The test statement is that you can make a test about the slope or some of the parameters in the model, and so we already know it's going to test something, whether or not the slope is equal to 0 or not. Here we can test for non-zero values, and we'll review this also. The beef cattle data in table 11.2 is what we're going to use in this chapter, and we'll see it in upcoming chapters as well. I have it listed in the book data sets where the SAS data step is already set up for us, and I'm referencing 5 columns of data, and that's these 5 columns, and then it repeats here. So there are 56 observations. What these stand for is the dry matter intake and the average daily gain of cattle. These are things that the producer has control of while the cattle are living at harvest. Then these are 3 measures that are obtained on the uh, animal after it is harvested, that is its carcass weight. You can get a measure of back fat thickness and ribeye area, and so these are ribeye area, the higher the better usually. Carcass weight, so you can see what we're looking these are listed here, I believe in pounds, so we're looking at a few hundred pounds of animal here for sure. In Objective 1, we're asked to regress the carcass weight on feed intake, or the DMI, and observe the default output. Use alpha equals 0.05 to interpret the significance of the slope parameter. So first of all, here's the beef data set up for you. Again, go to the datasets module in Canvas to see this. And so it's got all of those entered. Notice we have a few missing observations, not too many. And then in Objective 1, I've added the code here for what we need to do to get regress carcass weight on dry matter intake. So it's the language there is regress dependent on independent. So that determines the order here. Again, another way to think of it is independent. This is what we have pre-harvest, and this is post. So if we go through and submit this code, that's taken a little bit longer because I'm running recording software at the same time. We look that we have our 56 observations with 5 variables, and that we look into our procreg here, no errors. And so if we look at our results viewer, okay, up here at the top it tells me what my dependent variable was, the number of observations read and used. If there were any missing values, let's say for carcass weight or DMI in that list, then there might have read all 56 observations, but only 54 of them were usable or had complete pairs for carcass weight and DMI. Okay, so when we look here with our model, our F statistic is 49.88 and less than 1/10,000th. So this part up here is reviewing the model as a whole, and those of you familiar with multiple regression, you're going to move down here to read those. And so simple linear regression, we look at our regressor DMI, and so right now this 7.06, if I were to square this, I would get this 49.88. So that association exists in simple linear regression only. But the takeaway here is for our regression, then we do have a significant non-zero slope. Our slope parameter estimate is 13, and our y-intercept estimate is this 590 figure. So if we were to write the equation, it would be the predicted carcass weight equals 590.356 plus 13.105 times the DMI. So here the intercept, and then it's the coefficient of everything below that is what we're looking at. You get these diagnostic plots associated with your regression, and so that notice there are these residuals, here, and so whenever you plot your residuals versus your predicted values, you should see a random scatter. We've got a little bit of curve going on, and we identify a few extremes in here. Also, we had an assumption of normality, and so if our data tends to coincide with this 45-degree line, then we would conclude that we have normally distributed data. So we've got one or two values that are here, this negative residual, so that we have something that's a smaller animal, it looks like. And then it had the residuals here, residual by the independent. This was all by default information. We come here, and so that here is our line in the center of this blue band here, our confidence interval. Bands here are the for the mean response, and the dotted lines are actually then our prediction limits for an individual response. So prediction bands are sometimes much wider, as like we see here. They both are there. It's hard to see in the prediction bands, but they're narrowest whenever you're at the average value for DMI and the average value for carcass weight. That's X bar and Y bar are always on the line, and that's where those bands will be the narrowest. In Objective 11.2, we rerun the simple linear regression analysis, suppressing all of the graphs, producing 99% confidence intervals for each of the parameters in the model. Test whether the slope in this analysis differs from 9.2. Use alpha equals 0.01 in your conclusions. So when we write our code here, we can turn off the plots. We still have carcass weight regressed on DMI. We're looking for confidence limits on the betas, and that confidence level is going to be 99% since this alpha is 0.01. The test statement here, so we want to test whether that slope is something different than 9.2. So test, and just pick up the value here, equals 9.2. I called it slope 9_2, a period in the label, that it doesn't like those. And so then we'll look at what this does when we run this objective or submit this objective. So up to the top here, dependent carcass weight, using all of our data. Our test for whether it's equal to 0, that's still there. So this parameter estimates table previously stopped right here. So this is where it put the confidence limits for our intercept and for DMI. And then for our test, so that right here in the top test, slope 9_2, that's testing whether the slope for DMI is equal to 9.2 or something different. It's a 1 degree of freedom test, and so it does say that here in this F test we did come up with something different than 9.2. Pardon me, if we're at the 99% level, it's not. I'm thinking 0.05 in my head. At the 0.01 level, it's not different than that. This is also confirmed when you look at the confidence interval. 9.2 is in the 99% confidence interval, so those two pieces match. I apologize for the confusion there. As shown in the book, I didn't go through the details here, is that you can also test whether or not an intercept is equal to a specific value, and so here we tested whether the intercept was equal to 500 or not, and so this is the syntax you would use for testing the intercept. Again, you can use whatever you like here for the label. In Objective 11.3, we're to predict the carcass weight when the dry matter intake is 18, 20, or 22. We're to compute the 99% confidence intervals for the mean response and 99% prediction intervals. Use an ID statement, suppress all the plots. And so we want to go back and look at our table of data 11.2. Well, we've got the program up here. And so we have our DMI. We're supposed to make predictions at 18, 20 or 22. So I have a close to 18 in here, close to 20. So the one that's close up there, we could say, if by rounding, we may say that we have it, you can use this 18, but we don't have those exactly there. So how is it I'm going to make those predictions? First, I'm going to create a data set for this objective where I just put in those DMI values, the rest of, and I don't have to worry about anything else. Then I'm going to take and create a second data set where I'm going to take those 3 DMI values and I'm going to concatenate that with the rest of the beef data set. So I'm adding 3 lines with just DMI values. And then I'm going to look at, so I have beef 2 here, and then I'm putting that new data set into the procedure. I want to look at the fit plot here. I said suppress all plots, but I'm looking at the fit plot. And our model, again, carcass weight equals DMI. I wanted the CL, the prediction intervals, the confidence intervals for the mean response at 99%. And I'm using the X value or independent value in the ID statement, and we'll see why in the output. So if I take all of this, data step 2, because I haven't created that previously, and submit this. Okay. Objective 11.3. Okay. Number of observations with missing values, 3. And we created those. So that from this 3 lines, we can't be certain if it's carcass weight or DMI that's missing, but once we get going, we know it's the carcass weight that's missing because we did that. If we look at this table, it looks exactly like it did before. So adding those 3 DMI values doesn't change the regression equation. The regression equation is determined by complete pairs. And so if there's an incomplete pair, it's not influencing the outcome. So I can put that X value in there, that independent value in there, and not change any of this information over what we had previously. Now, because in the program I put the objective 11_3 at the top, and then at the beef data set, what that meant was that I put these 3 things at the top, and then the beef data sets carried on below. And so now then the dependent variables were what were the missing part. Now I get the y-hats or the predicted values, and so the ones I wanted specifically are right here at the top, easy to find. Likewise, I can get their means and confidence limits for the mean and the confidence intervals for our prediction interval. So they're not going to have a residual. The residual is the value between the predicted value and the actual value. And so here it's the difference between these two. We see is a little less than 6. That's 5.7. The difference between these two. That's what the residuals are. So you're not going to get residuals for these guys up here, but these first 3 predicted values or y-hat values then are very important. And so that's, again, stacking those 3 on the top or put them at the bottom, or even if you have those values in the data set somewhere, there might be merit to doing the stacking. Now the ID statement, the reason I said to include that is putting the value of DMI first. And so the reg procedure, what it does is it just starts with the dependent variable and goes across. So you never see these X's. That makes things very difficult to interpret, in my opinion. So almost always use the ID statement and put the X value here. Those of you with multiple regression, if you have multiple X's, list those in an order in the ID statement also. And that's I think a good habit to get into. And here I just selected the fit plot only, and so that image didn't change any over what we had before, other than our bands are 99% now. The core procedure is used to compute correlation coefficients between pairs of variables. So the simple syntax here is proc core with a variable statement, or you can use proc core with both of these statements, variable and with, and so it's either these two statements or all three of these. Of course, a run statement, and then you list the variables you wish to have in the correlation analysis. So correlation analysis is more appropriate when everything is a dependent variable. There's not this idea of this thing is a better predictor of this. They're both both variables are response variables. And so what we're testing here, when the correlation coefficient is near zero, we say there's no linear association. If it's non-zero, there's a linear association, and the correlation coefficient R is our sample estimate, and so it ranges from -1 to +1. So the closer it is to either of those endpoints, the stronger the association. The closer to zero, then there's no association. And this is a t-test, and it's a t-test with n-2 degrees of freedom in this application. On the proc core statement, we can request Pearson correlation coefficients. That's what it generates by default. Or Spearman is another type whenever we have lack of normality. If you want both of them, you have to request both. You can turn off all of the plots. Otherwise, your plot options are plots equals matrix, and so this sets up a scatter plot matrix. Well, it's better when we look at that in the objective to see what that looks like, or you can just look at plots equals scatter. So just they're not arranged in a matrix; they're larger plots. And you want to be careful that if you have several variables, they are greater than 10 variables, only the first 10 will be displayed in the scatter plots. In Objective 11.4, we want to test whether or not all pairs of the variables in the BEEF dataset are correlated. Produce the default scatter plot matrix. Use alpha equals 0.05 in your conclusions. And so we can do this, all 5 variables, in a VAR statement, disregarding that we have really kind of the independent and dependent association here. So if I pick those 3 lines up and submit them. So whenever you have a VAR statement alone, you get a Pearson correlation matrix. So you will always get simple statistics at the top for each of your variables, what the number of observations are, mean, standard deviation, the sum of all the observations, the smallest and the largest. So there's important information to be gained there. But if you just put everything in a VAR statement, you end up with a matrix. Since we had 5 variables in the VAR statement, we're going to have a 5 by 5 matrix. So each variable defines a row and column of this matrix. The header to this matrix up here is the legend for the contents of each cell. So it says it's the Pearson correlation coefficient, the probability greater than absolute R under the null hypothesis that rho equals 0. So it's giving me the p-value for the two-sided test is the correlation 0 or non-zero. And then it gives me the number of observations, which is the last number. Now, if we would have had the 56 measures for back fat and ribeye area up here, all those would be 56, and it would just tell us at the top that n equals 56, and we'd have only 2 numbers in the matrix. So that's how we go about reading those. We see the ones on the diagonal because everything is perfectly correlated with itself. And so this 0.743, that is the correlation coefficient between dry matter intake and ADG. So it's very strong and very high. Dry matter intake with carcass weights, less here with back fat, a 0.12, definitely not significant here, and with ribeye area at 0.59 we see an association there. And so that's how you go about reading these. So you can read ADG with any of these. Notice this ADG with DMI here is the same as above the diagonal, and you can do that with all of them. So this upper triangle, its mirror image is below the diagonal. So it's only necessary to read one side of this, of course. And so this can let us look at numerically where those strong trends exist. If we look at the scatter plot matrix, remember this order here: DMI, ADG, carcass weight, back fat, and ribeye area. And so what it's giving us is these scatter plots, these really strong association here between DMI and ADG. We've got this one observation out here. In practice, and we talk about this in chapter 20, we might have a look and make sure this was okay, and that we don't have a data entry error here, because we kind of have this one animal out here it shows up in just about all of the plots. I think he doesn't all of the plots. Okay, you can notice here where we have a very strong association and then a much weaker association. Over here I think there was no association, it's quite low. So whenever you tend to see things as more of a random scatter, that means that they are not correlated, or that supports that they're not correlated. A scatter plot matrix like this is getting pretty small, and so that you don't want probably to get more than 5, or I think it only stops at 5 anyway, because if you printed many more than this, it would be too small to be useful. Now in Objective 11.5 will demonstrate the with statement. We're not interested in all possible pairs of correlations such as we got here. Here we're interested in correlations of carcass weight with back fat and carcass weight with ribeye area. And so we can look at the scatters on those, and it wants to draw an ellipse, and so at this point I would recommend to turn that off or say ellipse equals none. So this is Objective 11.5. We have 2 width variables and 1 variable from the VAR statement. It gives us again those summary statistics. Gives us a table of the correlation coefficients, the top number being the Pearson. We have the probability and number of observations. So here it did put 54 in there twice, but notice it's back fat with carcass weight and ribeye area with carcass weight. If we would have reversed the roles of the variables in the variable and the with statements, then carcass weight would be over here, and I'd have 2 columns for back fat and ribeye area for those things that were in the VAR statement. So we get a much smaller display of correlation coefficients. You can double check that these numbers match what we had above in the larger scatter plot matrix. We asked for scatter plots and we got them, and they're a little bit bigger than we saw in the matrix. So we see all of our data up here. Again, we have this one little carcass weight 700, this one smaller animal here. So and that animal shows up here everywhere. Otherwise we can see this strong association here. And so we just have the 2 plots because we only had 2 correlation coefficients. In Objective 11.6, we're to compute the Spearman correlation coefficients for all pairs of variables in the set DMI, ADG, and carcass weight. Use a scatter plot matrix and include histograms for each response. So histogram is, if you go back and look at the plot options matrix, you can either do plots equals matrix or plots equals scatter plot. On the matrix you have a histogram option, and so we chose to include that. VAR, I'm looking at a subset of the initial 5, so DMI, ADG, and carcass weight. I'm looking at Spearman. Okay, we're looking at Spearman correlations. Remember, we have that one extreme animal in here, and so if the data look non-normal, so we're just looking at histograms for each of the response variables. We can see line here, having fewer variables in the scatter plot matrix. It's a little bit bigger than we had the 5 by 5 matrix earlier. We still get simple statistics here. It gave me the Pearson and it gave me the Spearman. So that actually is a little bit different than what since the last release. The last release is if you requested Spearman, that was all you got. So here we got both of them. And so in the Spearman, we can see this. It tells me up here n equals 56. So here's where I have common sample size everywhere, so it only puts the correlation coefficient and the p-value in each cell of the matrix. And again, we only have to look at the upper diagonal, pardon me, the upper triangle or the lower triangle to get those. So the Spearman correlation coefficient is computed using the ranks of the data, whereas the Pearson is using the actual data measures. So this is just a quick look at what the reg procedures and the reg procedure and the core procedure can do. And so if you're interested in examining the linear association between pairs of variables or looking at any kind of a predictive model, then these are the tools to investigate.